Okay, so this question asks us to uh, add three vectors. So our three vectors are already here. And another way of saying that is finding the resultant of those vectors. Now you'll notice that I don't have any specific vectors here in mind. Like could be a displacement vector, it could be a force vector, acceleration, velocity. It doesn't matter. The method is still always the same. So that's why I've said units instead of either meters or kilometers per hour or something like that. So once we've wrote down our givens, it's often a good idea to draw a little sketch. So we'll do that now. Make it blue. And so we have V1 is going east. So that's V1. V2 is going west 30 degrees north. So we start at the ending of our first vector. So it's going to go west and then 30 degrees north. And it's going to be a bit longer than this vector. It's 100. It's 20 degrees long. 20% longer. So that's V2. And then V3 is going east, but then it's going 50 degrees south, and it's a little bit shorter, so it's going to get kind of messy here. So what I'll do is I'll just put it somewhere like this. Now because I'm eyeballing it, we don't actually know for sure what's happening with the resultant, but if this is correct, then our resultant would begin where our first vector is, what began, and would end where our last vector ended. So that's our resultant, which is the sum of these three vectors. It's important to realize that we didn't actually have to draw them in order, V1, V2, V3. I could have drew V3 and then connected V2 at the end of V3 and then V1 at the end of that one, and then we would have gotten a line that was similar to this one here. So algebraically, what does that look like? Algebraically, to figure out the resultant vector, which we'll call Vt, so that's what this line is here, that's Vt, it's equal to V1 plus V2 plus V3. Now, if you look at these lines here, if I were to just straight add up these numbers, which are the length of these vectors is also called the magnitude. If I were to add these up, I would get 300. Now the length of this line is clearly not 300. So there's a different method for doing that. What we have to do is we have to break up each of these vectors into what's called its components. And so the first thing we do is we look at the components of each vector that are going east and west, or are along the x-axis. So for V1, that's easy because it is only going in the x, or in the east direction. So the x component of V1 is 100 units east. Now for V2, we'll just do a little quick sketch here of V2. For V2, going up like this, its x component is going west, so that's V2x, and then it has a y component that's going north, so that's V2y, and the angle here is 30. So it's interesting to note that a V2 is made up of the sum of its component vectors. You'll notice that the two components, V2x and V2y, they are following the rules of vector addition by aligning them tip to tail, and the resultant of that addition is the V2. So how do we get V2x? Well, we use a trig ratio. Because this is adjacent to this angle, we use the cos trig, or the Ka trig ratio, and that means that V2x is equal to V2 cos 30 degrees. And we know that V2, the magnitude of it is 120. And then the cos of 30 times 120, well, that gives us 103.92. And so if we go over here and we write that in our underneath our x-axis, we can put that as our magnitude. Now that will be going west, but we want everything to be going in the same direction. So what we're going to do is we're going to say that that's east, but it's negative east. And so we're going to do a similar thing for a V3. And we'll just, instead of drawing a picture, we'll just use the same idea. If we were to draw it, then it would be cos, because that's the side that's adjacent to the angle. And it's going east already, so we don't have to make it negative. So that would be 80 cos 50. And that works out to be 51.4 units. So we'll do the same thing for the y-axis. And once we've figured out the x-axis, the y-axis is actually, should be hopefully fairly straightforward. So we just erase this. Oh, let's move on. We'll put that over here. We'll put the y-axis down here. There we go. All right, so the y-axis, y. So for the first vector, it doesn't have a y component. So that's going to be 0. For the second one, if you recall, that vector is going up. So we just have to recall that that's going to be going north. So the way that we calculate that is we take 120 and it will be sine 30 instead of cos. So 120 sine 30. And that ends up being, should be 60 units north. And then V3y is equal to 80 sine 50. But that vector, if you recall, is going south. So it's going south. So that means that we're going to have to make our answer negative. So we'll do that here too. And our answer is 61.3 units north. So negative north is the same as south. Okay, so what we have here is we have all of the components of our vectors, and the idea is that if we add up all of the x components together, and then we add up all the y components together, what we'll get is we'll get a triangle that represents the triangle of our resultant vector. So let's look at this. So this vector, this is the x component of v1, plus the x component of v2, which is a line that goes backwards. So adding this to a backwards line will give us this little line. And then what we do is we add another vector going this way due to the v3, and that will get us this little bit right here. And it will be along here. Similarly, in the y direction, we'll be adding, well, 0, because there's nothing here, plus a vector that's going up due to this guy, minus, or plus a vector going down, which is the same as minusing the magnitude, and we'll get this little difference right there. See how there's a difference there? And so when we get this length and this length, then we can use Pythagorean theorem to figure out how long that vector is right there. So if we add, let's add the vectors together. And I think I can do the eraser like this. All right, so now let's do a different color here. Let's make it red. So I'm going to add up all the x components together, and we'll make a total x, which is equal to 100 plus minus 103.9 plus 51.4. And that's going to be our VTX. And then we're going to do the same for VTY, which is down here. And that's equal to 0 plus 60 plus minus 61.3. So if you go ahead and add those together, you get negative 3.1, oh, sorry. You get 47.5. So let's scratch that out. 47.5. And then here, you're going to get negative 1.3. So let's look at what that would look like as a vector. So if we were to draw that, then we would have a vector going to the east, 47.5, and then going a little bit south at 1.3. So our line that we're trying to find is this guy right there. And we also not only want to find its length, but we want to find this angle as well. So in order to find how long this is, we use Pythagorean theorem because we have two sides of a right angle triangle. So let's just erase that. And now we'll use Pythagorean theorem, where Vt, the magnitude of it, which is what these bars mean, is equal to Vtx squared, the magnitude of that, plus the magnitude of Vty squared. So if you go ahead and do that operation, you get 47.5. Now, we probably didn't need to do that because this one is so much bigger than the other one. In fact, in our little diagram here, I should have made the x line almost, 30 times bigger than the other one. So it makes sense that this would be pretty much the length of one of the sides. And then we can go on and find the angle. To find the angle, I like to use the inverse tan of Vty, the magnitude of that, over the magnitude of Vtx. And when we punch in those numbers, we get 1.3 over 47.5. And that ends up being 1.6 degrees. So, therefore, the resultant is 47.5 units. And then to figure out our direction, we go back to our components. It's going south and east because this is negative, so that means south. This is positive, so that means east. So then I use that information here, but I always start with the east-west one first. And the reason why I do that is because what I drew here. By putting the y on top, I'm essentially, it's going like this. So by putting the y on top, it's basically saying opposite over adjacent, right? Because that's what tan is. So this is VTY, this is VTX, so therefore I'm looking for that angle. So by doing it this way, that means I'm always finding the direction of my resultant with respect to the east-west line. So that would be 1.6 degrees south. Now let's see how does it even agree a little bit with our picture up here? No, we probably should have drew this a little bit longer. And then that would have gave us our correct picture.